Exercise set 1.4. Applications. Two-variable linear systems of equations. Standards of solutions. Define all variables. Explain the source of any newly introduced equation. Assess the correctness of the solution by performing two types of checks: a check of the math problem solution and a check for sensibility in the real world. Of the two checks, the latter is the more important. Be reminded that the most likely source of error in an application problem lies in the translation from the real-world problem to the math model problem, thus the importance of a sensibility check. Calculator usage is required. Exercise number 6. Tom and Jerry share the driving responsibilities for a 274-mile trip from Topeka to Dodge City, Kansas. Tom always drives at 76 miles per hour, while Jerry always drives at 87 miles per hour. The trip took 3 hours and 13 minutes to complete. How much of the distance was driven by Tom? By Jerry? Round each to the nearest tenth of a mile. Okay, let's see, for variables in this situation, what might be good? Okay. Maybe, since we are asked for the distances driven by Tom and Jerry, those could be okay variables. Alright, we'll try that. So let's let x equal the distance driven by Tom. And that'll be miles for the units of measure there. And then y could be the distance driven by Jerry. Miles for the units of measure there as well. Alright, what sort of information do we have that would translate into some equations? Okay. It's a 274-mile trip. Okay, so in other words, we've got a total distance is 274 miles. Okay, so from that we can say that the distance driven by Tom plus distance driven by Jerry has got to equal 274. Alright, there's an equation 1 we got. Alright, what other information that may translate? You might read, Tom always drives at 76 miles per hour. That's kind of an isolated little side fact. It doesn't seem to have an equation emanating from it. This Jerry always drives at 87 miles per hour. Same thing, sort of an isolated fact, not really translating to any kind of an equation. The trip took 3 hours and 13 minutes to complete. Okay. Let's see, let's think about that. Time of trip is 3 hours, 13 minutes. Okay. Now, a lot of times, as soon as you see information like, oh, the time is 3 hours and 13 minutes, what comes to your mind is that general formulation, distance equals speed times time. But you know what? You have to be careful with this. When we say distance equals speed times time, this is only true when the speed remains constant throughout the entire trip. Now, in this case, when we have this 3 hour and 13 minute trip, the speed changes depending on who's driving. If Tom's driving, it's one speed. Jerry drives, it's another speed. So, gotta careful. Only applies when speed is constant. Okay, so we can't really use this directly right on here. So we think of some other idea. Now, still, this information seems important. Time of the trip is 3 hours and 13 minutes. Okay, what we could do, we could think of this as a total time of the trip as being 3 hours 13 minutes. Alright. Just a slightly different perspective, but it might help us generate some equation now. So total time of trip is 3 hours 13 minutes. Okay. Now, where there's a total time means it's a sum of two times. And those two times would be the time driven by Tom and the time driven by Jerry. Time driven by Tom plus the time driven by Jerry have got to add together to be the 3 hours 13 minutes. Okay, now we haven't got a variable for time driven by Tom, but we do have a chance here to use the distance equals speed times time idea. At least over Tom's driving, the speed is constant when we only consider that situation. And so distance equals speed times time can be rewritten to say that time is equal to distance over speed. And now we can think of a way then to write, another way to write time driven by Tom. We can take Tom's distance divided by Tom's speed. Tom's distance, that's our variable x. Tom's speed, that's in the problem statement as being 76.0 miles per hour. Okay, plus, what about this time driven by Jerry? Use the same principle. We don't have a variable for time, but since time is equal to distance over speed, we can say it is equal to the distance driven by Jerry, which is y, divided by the speed that Jerry drives at, which is the 87 miles per hour. Again, just considering the time during which Jerry is driving, we can use distance equals speed times time because during just those times, the speed is constant. Okay, now, what about these two times? We said they were equal to 3 hours and 13 minutes. So now we have to get this in terms of hours. So 3 plus 13 over 60. Okay, here's an equation number 2. Right here. Okay, now, let's look at the, well, first make sure there's no other information that we didn't account for here. No, that looks like we're it. Here's our math problem. What about it? Look at these two equations, 1 and 2, both linear. Okay, so observe. Equations 1 and 2 constitute a linear system. So that's the kind of math problem we're into, and we're very proficient at solving these kind of math problems. The numbers seem a little messy, so let's go with a calculator solution. Equation 1, need to solve for y. Pretty easy. Subtract x from both sides. We could have a y1 equal to 274 minus x. And the second equation, let's see, we'll need to subtract x over 76 from both sides, then multiply both sides by 87. We would have y sub 2 equal to, okay, we got here 3 plus 13 over 60, and then we have a minus x over 76, and it's this quantity that gets multiplied by the 87. Okay, looks like we are ready to go to calculator. Okay, here at the calculator, let's go to the y equals 2 edit screen, and for our y1, we've got 274 minus x. For y2, we've got 87 parenthesis 3 plus 13 divided by 60 minus x divided by 76 parenthesis. Oh, I'm looking back at the y1 there. There is an x times x there. It's just one x. Let's delete that. Delete. Okay, that looks alright. Now, as far as picking a coordinate system here, since this is application, let's think about x for a minute. X is that distance driven by Tom. The total distance of this trip is 274 miles. So x has got a sensible range of anything between 0 and 274. So we could set up the window to have that in place. So x min could be 0. X max could be 274. And then we needn't fuss over the y-axis window. We can let the calculator just take care of that by going zoom fit. Zoom 0 is zoom fit. Okay, there appears to be a single point solution up in that upper left. Alright, not too clear. Maybe to look a little more closely at that, let's do some sort of zooming in. Maybe I'll try a zoom box in this case. In zoom box, you're supposed to pick the corners of your box, 2 diagonal corners of a box. Okay, I think I'll pick right there as one corner, and now another corner will be a lower left corner. Okay, maybe there. Okay, now I feel I really do see a clear intersection. Let's go get that with a second. Calculate and intersect. I like to sort of just get the visual on this curve choice. So I move to where my curves are clearly separated so I can get the visual as well as the expression in the upper left. Is this our first curve? I'll say yes by entering. And now I see the calculator cursor jumping over to the other curve clearly, so I feel a little more comfortable saying yes, this is the second curve by saying enter. And now I'll just go back to make a good guess at the intersection. That was around here. Enter. Okay, we've got this information here. I suppose it's time to take this back to our paper and start to interpret the math solution. Let's go. Okay, so looking at the calculator screen there, we have this x about equals to 40.4, and we have y about equal to approximating 233.6. Okay, now when we have our conclusion, we want to have something in words and interpret this. So back to what x and y are. This is driven by Tom and Jerry respectively. Okay, so now we can make a sentence. The distance driven by Tom is 40.4 miles. The distance driven by Jerry is 233.6 miles. Alright, this is the big conclusion of the question, so let's make sure this is very prominent. Okay, now that we have this, is it correct? Okay, let's check things over. Again, it's a two-part check. One is just checking the math, and the more important part, is this sensible or not? Okay, so first let's just take care of the math check here. For that, of course, you can't go wrong by going back and substituting into the original equations. Alright, so looking back at equation 1, its left-hand side is x plus y equals, let's see what that is, and the second equation has, although it has a constant on the right-hand side, it's, well, something that maybe we should compute separately. Okay, so here's equation 1. Here. Equation 2. We'll do it one side at a time. The left-hand side, LHS, is equal to x over 76 plus y over 87. That'll be something. And then we will want to compare that to its right-hand side, where it's equal to 3 plus 13 over 60. We'll get that as a single decimal number for a nice comparison between these two. Okay, back to the calculator. Here at the calculator, let's go back to that home screen. And first let's take care of this first equation, x plus y, x plus alpha y. Enter. 274. Okay, good. Now, the more complicated second equation, it's left-hand side. We got this x divided by 76 plus y divided by 87. Okay, have this number here. Let's get the right-hand side as a decimal. So 3 plus 13 divided by 60. Okay, they're equal. Looks good. Let's put this on paper. Alright, so the calculator's result of x plus y was the 274, just what we wanted to see. The left-hand side here, when we computed this x over 76 plus y over 87, it was, well, about equal to 3.22. And 3 plus 13/16 is also indeed about equal to 3.22. Left-hand side equaling the right-hand side makes that check. Math is in order. Now, is everything here sensible? What about this? Okay, what could we do here? Let's try to challenge this answer here with something that's simple or intuitive and see if it all is consistent. Let's see, what could we do here? Okay, since we have Tom's driving speed and Jerry's driving speed, why don't we consider a trip driven entirely by Tom, and then consider a trip driven entirely by Jerry, and see what kind of times we get. Because notice in our solution here, we've got the situation where we believe Jerry's driving the vast majority of this trip. So if this is the case, this trip should resemble, time-wise, something driven entirely by Jerry. Alright, well, let's see if this all comes together. So here's our sensibility check. If Tom drives the entire trip, the time would equal, okay, we're back to making use of distance equals speed times time. So in this case, we could have this equal to the distance over speed, which would be 274 divided by Tom's speed of 76. Let's get a number there on the calculator. And if Jerry drives the entire trip, the time will equal, which will be, in Jerry's case, 274 over 87. And then we also, okay, so first let's go get this on the calculator. Okay, here at the calculator, could clear the home screen up for a moment. And first you do the 274 divided by 76. Okay, we have that kind of time there in hours. And now to do 274 divided by 87, if you wanted to, you could go second entry. Since this calculation is so similar to the first one we did, we can just edit the previous keyboarding and overwrite the 76 with an 87. Okay. Alright, and let's go back to the paper with this information. Okay, so it looks like we found that Tom driving the entire trip, well, that would be about equals to 3.61 hours. If Jerry were to drive the entire trip, we're looking at about 3.15 hours. 3.61, 3.15. Now, the actual driving trip, actual time, was the 3 hours and 13 minutes, which we previously actually rounded this as a single decimal number to about 3.22 hours. Okay, 3.22, compare it to 3.61, 3.15. Well, it's actually very close to this 3.15, very much closer. Okay, so the actual time was this, which is much closer to an all Jerry trip than an all Tom trip, we might say here. Thus, we expect the majority of the distance to be driven by Jerry. And looking back at our proposed solution, 40 miles versus 234 miles for Jerry. This is indeed the case. Okay, so I think the solution now feels right, as well as passing the math check earlier. Okay. Exercise 8. A carat is a unit of concentration of gold, equaling 1/24th part of gold in an alloy. Suppose that a jeweler has some 18-karat gold and some 9-karat gold. What mass of each should be melted and mixed to produce 25 grams of a 16-karat alloy? Round to 3 significant digits. Okay, here the quantities that we might use to define as variables are exactly the same as the quantities that were asked for. The question eventually asks us what mass of each should be melted. Okay, how about letting x equal mass of the 18-karat alloy, or 18-karat gold. And, what units of measure would be good there? Surely grams, right, since the final alloy is in grams. Okay, and y could be the mass of the 9-karat gold, and grams there as well. Alright, how about some information that would yield some equations? Let's see. Well, here we're producing 25 grams of a 16-karat alloy. So 25 grams is the total mass. So the translation there is the mass of x, which is the mass of the 18-karat, plus y, the mass of the 9-karat. It's got to equal 25.0. Alright, there's an equation for us, equation 1. Now, what else have we got here? Sometimes you find that, especially in mixture type situations, and really a lot of situations way beyond mixture, but a conservation principle can be a great source of equations. Sometimes you find yourself using conservation of energy as a source of equation. Sometimes conservation of momentum will be your source of equations. And in this case, we could use conservation of gold, of pure gold. In this situation, we are just mixing and recombining these alloys. There are no nuclear reactions here, so the gold from the components has got to equal the gold in the final mixture. Okay, so let's write this down. Conservation of gold is the basic idea. And to elaborate a little bit here, the gold from the components, in this case those two alloys that are used to create this, has got to equal the gold in the final alloy. Okay, let's get the hold of the gold from these components. So this will be the sum of the pure gold from the 18-karat gold source. Now, how will we find that? Well, X is our mass of the 18-karat gold. Now, the concentration of gold within that X mass is 18 divided by 24. Okay, so we could have concentration 18 over 24 times the mass of the alloy. That's the gold in the 18-karat gold, plus similar idea for in this 9-karat gold alloy. Okay, the concentration is 9/24, definition of carat. There is a mass of Y of this particular alloy. Okay, so these two sum together. How about getting the gold in the final alloy? That final alloy is 16 karat, so its concentration of gold is 16/24. And how much of it is there? Well, 25 grams. Okay, got ourselves an equation 2. In this case, you may look at this equation and immediately say, oh, we could get rid of all these 24ths by simply multiplying both sides by 24. Okay, not a bad idea. Let's try that. 18x plus 9y equaling, now we have 16 by 25. Maybe I'll use parentheses. Okay, and this can become equation 2a. Alright, now as far as the math problem goes, oh, and we should make sure that we've accounted for every bit of core information that's in this question. The first sentence just defines caret. We describe the two alloys. The goal is to make this. Okay, no other information. Our math model is complete. These two equations, each of them is linear. Okay, so observe equations 1 and 2a constitute a linear system. Alright, so it's something we're proficient at solving. We could elect to go with a calculator, and in that case we need to solve for y in each equation's case. First equation, very simple, subtract x from both sides. y1 will equal 25 minus x. In the second equation, we'll need to subtract 18x from both sides, then divide by sides by 9. Y sub 2 will equal, let's see, 16 by 25. That would actually be 400, wouldn't it? So let's go ahead and take care of that now. 400 and minus the 18x, and then divide that by 9. Okay, here we are, ready to go to the calculator. Okay, let's go to the y equals 2 edit screen, and for our y1 we've got 25 minus x. For y2 we got parenthesis 400 minus 18x parenthesis divided by 9. Alright, now let's see here. As far as what coordinate system should we start off with? Since it's an application problem, x is the mass of 18 karat gold. We're creating this mixture that has 25 grams total. This would mean that no matter what, x has to be between 0 and 25. So maybe we set up a coordinate system that has that. Go to the window, x min 0, x max 25, and let the calculator worry about getting the y-axis set up so that the graphs entirely appear, which means a zoom fit. Zoom 0. Okay, we seem to indeed have a single point solution over there. Let's go get it. Second, calculate, intersect. First curve, yes, that one. Second curve, yes, that one. I guess over to the right a little ways. Okay, about there. Alright, let's see here. The question actually asks for rounding to 3 significant digits. So although it's tempting to convert these to exact fractions, it's not what we're looking for here. So we won't do that. Let's instead go right back to the paper with our decimal numbers right now. Alright, from the calculator, we have got this x about equals to 19.4 and y about equals to 5.56. Now I remember I have to round to 3 significant digits, so I need to record 1, 2, 3, 1, 2, 3 significant digits in each case here. Now don't want to leave this as my solution. I want to have a worded solution that has physical sense to it. This is called interpreting your solution. Don't just leave an X and a Y behind. Answer the question in words is best. And what does this mean? Okay, we use our own definitions to decode this. X is the mass of the 18 karat gold. Y is the mass of the 9 karat gold. Okay, so we can make a sentence. The jeweler should use 19.4 grams of 18 karat gold and 5.56 grams of 9 karat gold. This is the main conclusion of this question. I want to make it very prominent so someone reading this can just look at the bottom line if they are so inclined. But we do want to check this over, make sure it's correct. The instructions in this exercise set wanted 2 types of checks. First, math, then sensibility in the real world. Okay, for math here, what could we do? Well, we can substitute these numbers into the original equations, hopefully make them true. Okay, equation 1. The left-hand side had x plus y. Hopefully we'll come back with that 25 there. The second original equation, and the left-hand side of this is 18 over 24 times x plus 9 over 24y. And we'll see what that equals to. That will be the left-hand side. This is equation 1, this first one. Here's equation 2. This here is the left-hand side, LHS. We'll see what it is, and then we will take the right-hand side of this same equation, which is 16 over 24 times 25. We'll see what that is. These two need to be equal. Okay, little calculator action. Okay, at the calculator we can return to the home screen, and for equation 1 we have its left hand side, x plus y. Enter. Okay, good, that's the 25 we're looking for. The second equation, its left-hand side is got 18 x divided by 24 plus 9y divided by 24. Enter. Okay. The right-hand side of this equation is 16 times 25 divided by 24. Okay, great. Equals the left-hand side and right-hand side. All right, let's go back to our paper. Okay, calculator produced a 25 when adding x plus y. That's indeed the right-hand side of equation 1. Math check there. For the second equation, this was, well, about equals to 16.7, and this number comes out to be also 16.7. They are equal. Math check there. Okay, now, what about this answer as far as sensibility? Does this feel right? Okay, getting away from just the math, which could have a translation error, right? We need a sensibility check of some sort. Let's see, what can we do here? We're mixing together 18 karat and 9 karat, and we're to produce something which is 16 karat. Okay, you notice the concentration of this final mixture more closely resembles the 18 karat than the 9 karat. So we should expect to see the final mixture be dominated by 18 karat. Is that what we saw? And yeah, that's indeed what we see here. 19.4 compared to 5.56 grams. All right, so this is actually really looking pretty good. By the way, maybe I should say the very first sensibility check might be to, really it's the same as a math check. You want to at least see you have 25 grams overall. And when you just look at these two numbers, they, yeah, indeed pretty much add up to the 25 grams. So maybe first you might point out that total mass is 25 grams, which is, it was kind of the same as a math check in that sense, but still it's something that's also very common sensible. Okay, the other item here. Notice the concentration of the final mixture. Okay, we'll call it alloy. That's the name for a metallic mixture. Okay, the final alloy is 16 karat, which more closely resembles 18 karat than 9 karat. Thus, we expect a majority of the final alloy to be 18 karat. And again, there we have it. It's indeed the case. Okay, so now we can feel really confident about the correctness of this solution.